In this video, we're going to talk about the formal definition of a derivative, and we're going to sneak up on it in a way by talking about the slope. If you know anything about derivatives, you'll already know why I'm talking about the slope, but let's start with the slope and see where we can get. All right, now, when we had a straight line, there were various ways to calculate the slope. We could take the ratio of the differences in the y's to the differences in the x's. We could get the line in slope-intercept form and read the slope right off of it. But if we have a curve, it's a little bit more difficult. So let's look at a curve and let's get started. So this curve right here happens to be y is equal to x squared plus 1. And the good people in Desmos are letting me use their graphs, so I want to give credit where credit's due. And let's say that I just want to talk about the slope at this point right here, which is 1, 2. And I want to calculate the slope at x is equal to 1. Well, I don't know how to calculate a slope at a point. I know how to calculate a slope between 2 points, but I don't know how to calculate a slope at a point. But there's a way, and we're going to explore it. Okay, so let's say that I had a second point over here. I could find the slope between these 2 points, and it looks like it might be kind of close until you blow it up and realize that it's approximately in the general area of that, but this slope is probably more like this if we just kind of estimate it based on the curve. So it doesn't seem like it's going to be the slope. It may be close to the slope, but it's not the slope. So not to be outdone, there has to be a way. And here in just a little bit, I think it's going to start occurring to you what we're doing. So right now we have this point 1, 2. And we have some point over here. It could be 1.5 and some number y. It could be 2 and 3. We could start at 2 and 3, but that's way over there. Definitely not what we're trying to do. So I need some generic point pretty close to 1, 2, and see what we can do. Now, what we would have done is using this slope formula over here, we would have had a second point over here. And this would have been our first point. And we would have said, oh, I can calculate this value x2 for whatever point you want using that formula. So given an x, I can calculate a y. Then I could put the specific y2 here and put its corresponding x2 below it, and then y1 and x1. And I could calculate a number. Looks like it'd be a positive number, but I can calculate a number. This sets up a little right triangle. So this distance right here is y2 minus y1. And this distance right here is x2 minus x1. Okay? Now what I would want to do is to get x2, this is x2, I would want to get x2 closer and closer and closer and closer to x1 until it's just like right on top of it, not quite. So I'm going to go from here to here to here to here. So I'm moving x2 closer to there. Is this kind of sounding familiar from your limits section? So I'm trying to move x2 closer and closer to x1. Okay, with me so far? Let's go back to our little triangle. Okay. And rather than calling this x distance right here x2, x1, and the distance would be x2 minus x1. That would be the distance, right, between the two. And saying the difference between the two is getting smaller and smaller, smaller. Let's just call this h. So whatever that distance is from here to here, we're going to call that h. So what that would be is this is x. You can think of it as x1 or just some generic x. And this distance over to here would be whatever your original x was plus some distance over, right? So if you have some point that you're curious about and you go some distance h over, this would be x plus h. Now, let's talk about the ordered pair. If we don't know that we're going to do 1 and 2, we're going to do generic point. Whatever this x is, the y that goes with it is f of x. So this ordered pair is whatever x is and the y that goes with it, which is f of x. Okay? And this ordered pair right here is whatever its x is and whatever the y is evaluated at x plus h. So my two ordered pairs are not 1 and 2 anymore because we're going to do this for a generic point. X, comma f of x, and x plus h, comma f of x plus h. Now, let's do this slope formula with that. So we would say the slope is y2, which is f of x plus h, correct? F of x plus h, minus y1, which according to our drawing would be f of x, over the x of the second point, which is x plus h, minus the x of the first point, which is x. Okay? And we're trying to make h get as small as possible so that the second point is as close to the first point as we can get it. And as you get closer and closer and closer to it, you are taking a limit as h approaches 0. And in some of the other videos like the one especially over complex fractions and taking the derivative, I mentioned that you'll get really familiar with this h approaching 0. Now, let's clean this up a little bit. So it's the limit as h goes to 0 of f of x plus h minus f of x over, and x plus h minus x, the two x's fall out. And it looks like this. Look familiar? Okay. And this is the slope. You okay so far? So the slope for any function in terms of x is f of x plus h minus f of x over h as h goes to 0. Okay? So for our function, if you have y is equal to x squared plus 1. Let's see what this gets for you. So the slope at any point in the graph, not just a specific point, but any point in the graph is, according to what we derived, the limit as h goes to 0 of. Now, I want to give you a few kind of little hints. This denominator is always h. It's not anything else but an h. It's not 2h. It's not 3h. It's not h plus 1. It's just an h. So you might find it easier to start at the bottom of the fraction and work your way around to the top counterclockwise because you're going to have to do a few of these. So we move up to this little spot right here, and this spot is f of x. It is always f of x. And that means it's always your original function. Whatever your given function was, it's this one. So this part down here is always the original function, as is. So you don't have to spend a lot of thought on it. You just copy in your original function. Now, this part takes a little bit of work. So if you had f of x is equal to x squared plus 1, and if you had said, what's f of 3, you would put 3 in right here and go 3 squared plus 1 is 10, right? Well, we're not asking you to do f of 3. I'm asking you to find f of x plus h, but you do the exact same thing. You're going to put x plus h everywhere there's an x, so you put it in there, you put it in here, you leave everything else the same. So this x right here gets replaced with x plus h. The square stays the same and the plus 1 stays the same. All you're doing is replacing the x, this one too, with x plus h. So the only part that actually makes you do some preliminary work is this x plus h squared plus 1 part. And this is always a minus. This is always a minus. So this front part right here, this part, is a part you have to kind of set up. This is always your original function, and this is always h. Okay, now let's see what we can do here. So this is m equals the limit as h goes to 0, and we can expand this out. So x plus h squared is x squared plus 2xh plus h squared plus 1, and we're going to subtract this x squared and this 1, so it's minus x squared minus 1 over h. Now you'll know if you do this part correctly because all the terms that do not have h will cancel each other out, okay? So this x squared and this x squared go to 0, and this one go to 0. Everybody else still has an h, which is making me feel good about what I just did. It doesn't guarantee you're right, but it does help you feel better. And you'd have 2xh plus h squared over h. There's an h in common in the top, so we're going to factor that out. And then this h cancels out that h, gives you memories. I don't know if they're good memories or bad memories, but it gives you memories of limits and transforming them. All right, and then we'd have the limit as h goes to 0 of 2x plus h. And now we can substitute in h is 0, so m is the limit as, okay, so if you go ahead and substitute this in, you'd have 2x plus 0, so this is 2x. Now, what that says is whatever slope you have for whatever point you want, you can just calculate it. So if x is 2, the slope is 2 times 2, which is 4. If x is 3, the slope is 2 times 3, which is 6. If x is negative 1, the slope is 2 times negative 1 is negative 2. Now, our particular question was, what if x is 1? So m is 2. And just for me, I want to do one more. If x is 0, 2 times 0 is 0. So I want to talk about these two right here. Okay? So what we found is that with the slope at this point, the slope is 2. That seems kind of reasonable right here, I think. But the one I really want to talk to you about is right here. So when x is 0, the slope is 0. And that sort of makes sense. On this side, the slopes are negative because they're going downhill. On this side, the slopes are positive because they're going uphill, right? So right here in between, you go from negative to positive, and you go through zero right there. Okay? So what they have decided to do is to say the instantaneous slope at a point for a function is this limit as h goes to 0 of f of x plus h minus f of x over h, and instead of calling it m, they're going to call it this f with this little dash right here. So this is called f of x. This is called f prime. And that would be the derivative of f. Okay? So the derivative, this is the formal definition of the derivative. If it exists, okay, because sometimes, remember, we couldn't get the h to disappear, so we'd have 0 in the denominator, have all sorts of troubles. Okay? So if it exists, this is the derivative of your original function, sometimes referred to as f prime. And again, what it gives you is a lovely formula to calculate the instantaneous slope at any given point. So this is, remember, the instantaneous slope. This original setup here, when we first started talking about it, where we had y2 minus y1 over x2 minus x1, and there was a definite gap between the 2 points right here. This is called an average. This is an average slope, or in calculus, they typically call it an average rate of change. So if they are looking for an average rate of change, they are asking you to go back to the original algebra definition and use this y2 minus y1 over x2 minus x1. Okay? If they say something about the derivative or the instantaneous rate of change, they are talking about this f of x plus h minus f of x over h as h goes to 0. And in future videos, we're going to find shortcuts on how to do this so we don't have to take quite this long to calculate it. If you already know the trick on how to calculate it, don't share with everyone else, because if your teacher's going through this, you're going to have to do something on your homework and or on the test where you have to give, using the formal definition, you have to go through this algebraic manipulation. And if you just do the shortcut and tell your teacher what the derivative is, they will not give you credit. Now, you can use the shortcut to check yourself, but you have to do it the long way. So in the description below, you'll find some practice problems to do and a link to the next video. And I just wanted to remind you of that. But I'm going to do a couple of more, probably 3 more problems just to show you how this works before we end this video. But we'll come back to that idea about the formal definition. Don't forget about the links below. And we'll start in just a second. So you might get a drink of water or something like that, and then we'll do another one or 2 or 3. The first problem I want to try is a polynomial. For a polynomial, the domain is all real numbers. So any x that you are curious about that is a real number, you can find this instantaneous slope, otherwise called a derivative, and then substitute in that value for x and evaluate it to find the slope at a given point. All right, so let's get busy. Using the formal definition, you have f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And if you'll write that down every time you do a problem, you'll have that memorized a lot faster than if you just sit there and stare at it and read it to yourself. Now, as you fill this in, you have to write this limit as h goes to 0 on every line. Remember that the h is always an h in the denominator. This second part right here is always your original function, and it always has a minus in front of it. So the original function is x squared minus 2x cubed. And the part that you have to do some mental work to decide what it is this front section where you look at f and everywhere you see an x, you replace it with an x plus h. So you would have x plus h squared minus 2 times x plus h cubed. The x's get replaced with x plus h. Everything else stays the same. Now we have to expand this. So it's the limit as h goes to 0. And x plus h squared is pretty familiar. We've done that a lot since algebra. So this is x squared plus 2xh plus h squared. This other part is a cube, and you can multiply it out and say, okay, it's x plus h times x plus h times x plus h, and you can multiply all that out and group up like terms. But if you know the binomial expansion, then it goes like this. So if you have x plus h cubed, the highest powered term in the front is going to be x cubed with no h, and the term in the back is going to be h cubed with no x. So you have the best way to build this is to go, all right, I start off with x cubed, go to x squared, because you stair step down, x, and then no x's. And then going from the back to the front, I have h cubed, h squared, h, and then no h's. But then you've got coefficients and possibly in front of each one. Some of them are understood ones and don't really show up, but they're still there. And you get that from Pascal's triangle. And you started off with this group of ones right here. These two added together to make 2. These two add together to make 3. These two add together to make 3. And since you have a power of 3, these are your coefficients. If you had a power of 2, this is your coefficients. If you had a power of 4, it'd go 1, 4, 6, 4, 1. Okay? So this is 1, 3, 3, 1. That's a little faster than having to multiply that out 3 times. So this is minus 2x cubed plus 3x squared h plus 3xh squared plus h cubed. Now, just to kind of show you, do you see how this does the same thing? It's x squared x and then no x's versus h squared h and then no h's. And the coefficients for that one are 1, 2, and 1, so they all go that way. We just have this one kind of memorized from a past exposure. All right, so this is h cubed. And don't forget to subtract your original function. Okay, all of this over h. And as you can tell and kind of guess, if you make a math error in here, It's really hard sometimes to find it. But it's good experience, and because not everything is clear and has a quote unquote trick in order to get it done. So we have got to find a way and get our math skills dusted off. I forgot to close this parentheses. All right, let's keep going. Now, when you kind of leave this blank right here, it's understood it's still f prime equals, but you have to keep writing the word limit, right? So we have x squared plus 2xh plus h squared minus 2x cubed minus 6x squared h minus 6xh squared minus 2h cubed minus x squared plus 2x cubed because the negative distributes. Okay, now if we're doing this and I want to feel kind of good about what we're doing, everything that does not have an h should cancel out. So this x squared and this x squared go to 0. And this minus 2x cubed plus 2x cubed goes to 0. Everybody else has an h. I don't see any other like terms. Okay, so what we have is the limit as h goes to 0, but they all have an h in common. So it's h times 2x plus h minus 6x squared minus 6xh, because I took an h out, minus 2h squared over h. So what I did between here and here is I factored out an h. So these two h's cancel. And I have 2x plus h minus 6x squared minus 6xh minus 2h squared. And that h that was in the denominator that kept me from actually substituting in h is 0 is now canceled out. So I can put h is 0 in all of these locations. And I would have 2x plus 0 minus 6x squared minus 6x times 0 minus 2 times 0 squared. Now, you don't have to show that step, but when you get rid of all the zeros, you have 2x minus 6x squared. And this is the derivative and the instantaneous slope. Okay, let's do another one. Let's do one that's a little bit more complicated for a square root. So you remember one of the other kinds of limits we did was what if there were square roots in the problem and we had to multiply it by its conjugate in order to get it to reduce in order to take the limit? Well, this one doesn't necessarily look like a square root, but remember this is the square root of x cubed if you wrote it as a root as opposed to a power. So I want to find the derivative, or they could have asked me for the instantaneous slope at some particular point. And so this is the limit as h goes to 0 of f of x plus h minus f of x over h, because we're going to memorize it. So f prime of x is the limit as h goes to 0 of h is always h. This part at the end is always your original function. All right. This part at the beginning is your original function, but everywhere you see an x, you replace it with an x plus h. So it looks like this. Now, it doesn't have the lovely little square root sign in it, but these are square roots. So in order to try to be able to have h go to 0, and it's not in the domain of this function right here. Maybe I can multiply it by its conjugate. All right, now the conjugate would be the same two terms, but the sign in the middle is different. So since it was a negative, it's going to be a plus. All right, here we go. So it's the limit as h goes to 0 of. Now let's look at the bottom, and you've got h times x plus h to the 3 halves plus x to the 3 halves. Okay, it is not to your advantage to multiply this h across because I actually want the h to be canceled into something on the top so I can make it go away because this h is giving me 0 on the bottom. So I don't want to entangle it with these two pieces. I want it to go away. So leave it alone so maybe we can get it to cancel. Okay. Now, this top part, right, let's look at it. These are conjugates, so I will get the difference of two squares. So these two are x plus h to the 3 halves squared minus these two, which is x to the 3 halves squared, because I know the middle terms are going to fall out. We did all this in the limit section. I don't need to see that anymore. We actually did it in the review section too. So let's just cut to the difference of two squares. All right, and when you take powers and you have something like x cubed squared, these two multiplied, right? And you'd had 3 times 2 is 6. Remember that from your basic properties of exponents? So these two are going to multiply. And 3 halves times 2, you can think of it as 6 halves, or the 2's cancel, and this is going to be x plus h cubed. Okay? Minus. And then when you look at these two, the 2's cancel, or you can think of it as 6 halves, it's x cubed over h. So this is the limit as h goes to 0. And we just did this one. Okay. Up in here where we were looking at the 1, 3, 3, 1. And it was this right here. X plus h cubed. So using that, you would have x cubed plus 3x squared h plus 3x h squared plus h cubed minus x squared. And again, what you're really hoping is that anybody that does not have an h gets canceled out by somebody else that's the opposite that doesn't have an h. And here's thus. Everybody else has an h, so I'm going to factor the h out while I'm writing down this next step. So I have h times 3x squared plus 3xh plus h squared. Oops. I dropped off my part right here. Hope y'all caught that. I'm not going to redo this whole tape for this. I am going to tell you what teachers always say in a public setting when they're doing that. They go, I just did that to see if you were looking. And that always translates to, I lost my mind for a second. Okay. And I really wasn't seeing if you were looking. I just lost my mind for a second. All right. So this is still H, and this is still dragging along. I've written all these out, and when I looked over to double check I was still on my path. I went, oh, where did my denominator go? All right, so here we go. So this h cancels this h. Otherwise, I would have had nobody down there but a 1, and that wouldn't have worked. All right, so I want to make h go to 0. So you'd have 3x squared plus 3x times 0 plus 0 squared over x plus 0 to the 3 halves plus x to the 3 halves. You okay with me now so far? All right. And next time your teacher says, I was just seeing if y'all were paying attention, you can just smile and know that they just got distracted for a minute. That happens. Okay, 3x squared. Okay, now on the bottom, I have x to the 3 halves plus another x to the 3 halves. So I have 2x to the 3 halves. Y'all hanging in there okay? All right, so this is the limit. Okay, now there's no more h's left, so you don't actually have to have that limit there. I was hung up on trying to explain my way out of where I lost the denominator. You don't actually have to have that. It's not going to kill you. But when you get ready to have the end of the problem, there's no more h's left. There's no more limits. And so this is 3 halves, and you have x squared over x to the 3 halves. And if you remember your exponential rules, it's 2 minus 3 halves, right? Start with the top and subtract the bottom. So this is 3 halves x to the 1 half. Y'all doing okay? And this is f prime. Now, I want to talk to you for just a second about good form, okay? You could also think of this as f prime is equal to 3 halves square root of x or 3 square root of x over 2, right? But good form is actually, let's look back up here and see how they gave it to me, okay? And what they gave it to you as was x to the 3 halves, not a square root, okay? Not in this sense of a square root. So it would be bad form to return it like this because that's not the form that they gave it to you in. So they gave it to me in powers, so I'm going to give it back to them as a power. Okay? One more, I swear it, and then we'll be done. All right. So let's do the f of x is 5x over 1 plus x squared. I know I couldn't let you go without doing a complex number fraction one. Okay, so the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h as h goes to 0, right? So it's the limit. Okay, h is always h. This last function is always just itself. Okay, this is always a minus. This front piece right here is always whatever your original function was, but everywhere you see an x, you replace it with an x plus h. Okay, now here's a lovely complex fraction. You can think of this as over 1. Some people don't want to think about it as over 1, and some do. But what we're going to do is to come up with our least common denominator and multiply all 3 pieces by that. If you are doing the other alternative method where you combine the numerators into one fraction and then divide by what's on the bottom, you either need to go back to the limits section on complex fractions, or I'll try to remember to put a link in here, a review for how to do complex fractions, because these get really bad really quickly. You don't want to do it that way. So the least common denominator is 1 plus x plus h squared times 1 plus x squared. That's your least common denominator. Okay, so we are going to multiply this top and bottom by, oh, my Things just stopped writing. All right, we can do this. Okay, by 1 plus x plus h squared times 1 plus x squared. And what you multiply the top by, you have to multiply the bottom by. I hope y'all don't mind my kind of weirdo sense of humor every once in a while. I've always done that in classes because it just makes the day go faster, and I can't resist doing it on these videos. So let's see what we've got. This entire least common denominator is going to multiply this and also this. And so what I suggest you do, if you're anything like most of the students, and I sometimes have a tendency to do that when I was learning, is since you know I need this entire denominator to multiply not just this fraction, but the other one, you might want to squeeze it over here just so that you can see it. And also so that you can cancel out appropriate parts. Because you don't want to have an error this early on. Okay, so looking at this, and you have to do the denominator, but that's right here. Okay, so let's not forget that. Now, so this 1 plus x plus a squared cancels out this one. All right, and you have the 5 times x plus h that you started with times this 1 plus x squared that is left right here. Okay, then this 1 plus x squared cancels this one, and you have 5x times, so this is going to multiply this part that's still left, 1 plus x plus h squared. And in the denominator, you have h times 1 plus x plus h squared times 1 plus x squared. Now again, do not multiply this out. You're hoping that you can make the h go away because that's what's giving you 0 in the denominator. So let's do some massive cleanup. All right. So from the first, you would have 5 times x plus x cubed plus h plus x squared h when you distribute that, okay, minus 5x times 1 plus x squared plus 2xh plus h squared over all of this. And if you leave any of this off, your teacher will count off for skipping steps. It's good for self-discipline to put all this in there. All right. So then when you clean this up a bit, you have 5x plus 5x cubed plus 5h plus 5x squared h minus 5x, because we're down to this part where we're doing this, minus 5x minus 5x cubed minus 10x squared h minus 5x h squared all over h 1 plus x plus h squared, 1 plus x squared, right? Now, like usual, makes me feel good when everybody that doesn't have an h goes away. And I'm going to factor out the h while I'm writing this next line. So you would have h times 5 plus 5x squared minus 10x squared minus 5, that's from h. Nope. 5x squared minus 10x squared minus 5xh over h. There is a lot to write. I'll grant you that. So this h gratefully goes to 0. And I'm going to make the rest of these go to 0 while I'm here. So you'd have 5 plus 5x squared minus 10x squared minus 5x times 0 over 1 plus x plus 0 squared times 1 plus x squared. Okay, so this is 5 plus 5x squared minus 10x squared. Now, are you going to be okay if we just sort of clean that up right there instead of writing it all out? Would you be all right if we went, okay, 5x squared minus 10x squared is minus 5x squared plus 5. You okay with that? Okay. And then down here on the bottom, this is actually 1 plus x squared times 1 plus x squared, right? This part. So this is 1 plus x squared squared. And that's the derivative. Okay. Now, interestingly here, this is a pretty complex problem, but what's nice about this is I don't even have to know what it looks like. If I want to know what the slope is, let's say or the tangent line to a curve, I could say what's the slope at x is equal to 2, let's say, right? So remember this is the slope at a point, so you'd have minus 5 times 2 squared plus 5 over 1 plus 2 squared squared. So you'd have minus 20 plus 5 over 5 squared, which is 25. So this turns out to be minus 3/5. So even without graphing it, I can come up with a slope. We haven't talked about tangents yet, but we will. And so that helps me get started. All right. Now, so this is a lot of math. This is a lot of algebra. The things that drive calculus students is not the actual calculus part. Okay. This right here, is the calculus part. All right. And you're not even really applying calculus rules, but that's the calculus part. All the rest of this, all of this is algebra. So all of that gives you a chance to make an algebraic error, and that's what counts off points here and there and everywhere, causes problems, sometimes makes the entire answer wrong. Sometimes students take a wrong turn because they're not comfortable with the algebra. So the algebra is the part that is really the biggest contributor to errors. And if your algebra is weak, I strongly suggest that you go back and do some problems with your algebra to toughen those up. If you need some reviews on square roots, multiplying by conjugates, or complex fractions, I will put a link to those reviews in the description, down below in the description. So if you need some practice with those, you can go back and look at them. And I hope all of this helps. So go and look at the description, follow the links, like the video if you do like it, subscribe if you want to. I will talk to you later.